soap bubbles we are used to typically aren't blue. They are rainbow colored and they can be more or less transparent. My name is Paola Rebusco. I am a theoretical astrophysicist here at MIT. In the previous Blossom modules about soap bubbles, we were investigating the basic nature of soap bubbles and their shapes. Today, we will find out everything, or as much as we can, about the color of soap bubbles. Also, did you know that soap bubbles and telescopes have something in common? We will understand what this is. Moreover, we will see that blue bubbles actually exist, and we will try to understand what is the difference in the color between the blue and the usual bubbles. Finally, if you watch a soap bubble for a certain amount of time, you may notice that the colors and the patterns on the surface change over time. And this can have something to do with the large-scale motion on the atmosphere of the Earth and other planets. In order to understand the colors, we first must have to make the connection with light and waves. So let's start making some waves. Here I have a salad spinner filled up with plain water, and if I poke my finger in the center, you can see one ripple, one pulse that is moving outwards and then coming back because it reflects on the wall. I can do it many times at a periodic rhythm, and you can see waves on on the water in the salad spinner. Now, it may be a little bit difficult to see the waves for you because there is the camera in a difficult position. However, you should try to do this in the classroom, and if you look from the right position, you will be able to see the ripples and the waves moving in different directions. You can also try to create waves using a very long rope or a spring. So stop the video now and see you soon. Welcome back. Now that we know how to create some waves, we want to look at their anatomy. So what is a wave? A wave is a perturbation that travels in time and space. A transverse wave is a wave that is oscillating in one direction and is traveling in the perpendicular direction. So here, for example, I have a spring, and I can perturb it in this way. The perturbation in this direction is creating a pulse that is traveling in the perpendicular direction. If you look at the black tape in the center, you will notice that it's just moving back and forth. It's not actually moving with the wave itself. Let's look at this in a drawing. Here we have the displacement in function of the distance from the origin, the distance from the place where the perturbation is taking place. We call amplitude the maximum displacement of a wave, while the crests and troughs are the highest and lowest points reached by the wave. The wavelength is the distance over which a wave repeats itself. For instance, it is the distance between two crests or between two troughs. You may have noticed when you were trying to create waves in the classroom that when you were increasing the frequency of oscillation, then the wavelength, the distance between crests, was decreasing, and vice versa. Why are we talking about waves? Well, light is an electromagnetic wave. Other electromagnetic waves include microwaves, radio waves, and X-rays, for example. Electromagnetic waves originate from the oscillation of the electric and magnetic field. We cannot see this field oscillating, but we can see the resulting light. So, now you will try to create a rainbow in your classroom. You can do this using a LED or a flashlight and a bowl full of water. And you need a lot of dark. So please switch off the video and the lights and see you soon. Well done! You decomposed light. Indeed, white light, what we call usually the normal light, is composed actually by all the different colors. But what makes these colors, these waves, different? This is the wavelength. Indeed, the wavelength of the red light is larger than the wavelength of the violet light. And the other colors have wavelengths in between. So here, from red to violet, we have decreasing wavelength, which means increasing frequency. This distance, in reality, is really, really tiny. It's of the order of 100 of a billionth of a meter. A billionth of a meter is called a nanometer. Now, when you are shining the light through the water, what happened was that the different colors, the different wavelengths, were bent. In scientific terms, we say refracted at different angles. This is one way to decompose light. But we can do it also in another way. For example, let's use a black mug or a film can and dip it in a soapy solution. We want to create a film here. And we want to look. Now the film exploded, so I'm going to do it again. And you can notice two things. First of all, you can notice that there are many different colors. And second, you see that there is the reflection of the ceiling in this case. Try to do this in the classroom and take careful note of what you see, what are the patterns, and what are the colors. Welcome back! I hope you had fun playing with the thin film in a black mug and that you observed the horizontal bands of colors and how they change in time. Here we have a nice photo of a thin film when you can see all the colors. But where do they really originate? We said that colors are light, and light is electromagnetic wave. Waves travel in time and space. They can bounce off some obstacles. If they go through a different media, they get bent, they refract. And if they meet at the same position, they can interfere. Interference is at the origin of the colors in soap bubbles. For example, we can have constructive interference. When we have constructive interference, the crests of two different waves match, and the troughs match the troughs of the other wave. The resulting wave will be reinforced. We have an amplitude which is higher than the two incoming waves. Destructive interference occurs when two waves meet at the same position, but they are out of phase. So we have that the maxima meet with the minima, and vice versa. And if they have the same amplitude, well, the resulting wave will be nothing. They cancel out. And this is a very weird phenomenon, because we have light that meets other light, and the result is something dark. Now, Now, in this drawing, there are two extreme situations. In reality, there will be all the situations in between. If we look at a soap bubble, what is happening? We said that soap bubble can be thought of as a sandwich of water in between two slices of soap. So when we have an incoming wave, let's say a purple light, it will reflect on the first external surface, and then part of it will be transmitted through the water and to the second surface, where it will be reflected again. And here, of course, there is a little part which is still transmitted. So the two reflected waves will meet at the surface, and they will interfere. The interference can be constructive, and so we will see the colors more intense, or it can be destructive. When we consider a soap bubble, we look at it and we look from different angles. Moreover, the thickness is not the same everywhere. So what happens is the different waves, the different colors, walk through different paths. And so when they interfere, the difference between the wavelengths and how they compare to the thickness of the soap film will originate different colors. And this is where all the swirling colors of soap bubbles take place. Now, in the classroom, you will investigate interference